If we have any spotlight presenters anywhere in the back, please come up. We have spaces here for you. We only have about half of the spotlight presenters up here at this point.
So good afternoon. Welcome to the session for image motion and tracking. I'm Katerina from CMU.
And Nathan Jacobs from the University of Kentucky.
We're going to start with 3 oral presentations. Each one is 12 minutes long, and we have 2 minutes for questions. The main presenter for oral 2, please to come in front. The spotlight presenters, please to come line up as well. And we're ready to start.
Okay, our first presenter is going to be Deqing's son.
Okay, thank you. It's a great pleasure to talk about our work on optical flow. It's joint work with my colleague Xiaodong Yang, Ming-Yu Liu, and Yang Kautz. The goal of optical flow estimation is to predict a 2D motion vector for every pixel from one frame to the next, as shown in this color representation. A recent influential work is Florence 2. It shows like a fully end-to-end CNN model can perform very close to the state-of-the-art. So here the y-axis is the endpoint error, smaller better, and the x-axis is the running time. As we can see, although there is still some performance gap between Florence 2 with state-of-the-art, well-engineered approach, but the running time is much faster. Looking at the plot, you may wonder whether it's possible for a fully end-to-end CNN model to outperform the state-of-the-art, but still run fast. So that would be an ideal algorithm. So let's see all the published CNN models for optical flow. In terms of performance, the y-axis and the model size, that's number of parameters in the x-axis. We can see there is a clear trend between the performance and the model size. It seems like we are going to use a bigger model than Florence 2, which is already big with 160 million parameters and hard to train. And so, to some of your surprise, I'm going to present PWC-Net, which is very compact but still highly effective. It actually outperforms state-of-the-art on the Intel final pass. And so what's the insight? The insight or the key is to make frequent use of the domain knowledge to build the network. So what do we know about optical flow? Next, I'm going to review some of the basic principles, which is the prior work also used to build the network, but how our network use them differently. The fundamental assumption for optical flow is brightness constancy. It means a pixel will return its brightness or some property over time, despite its position change. So based on this assumption, we can actually build a very simple algorithm to get some intuition. So the algorithm works like this. For every pixel in the first image, we crop a patch. And then we exhaustively compare it with every other patch in the second image. We can use normalized cross-correlation to compare the patches. And here is the response. The brighter means more similar. As we can see, there is a very strong peak near the true motion. So the algorithm actually is constructing the Kautz volume, which is widely used for stereo matching. So the Kautz volume stores the cost, or in this case, the similarity of all the motion vectors for the current pixel. A nice property of using correlation is it has some invariance to the changes in the color. So for this one, we actually make the image darker or brighter. As we can see, the peak of the correlation remains constant. And so the Kautz volume has been widely used for stereo, but not for flow. Why? There are two issues. The first is it's very computationally expensive. Recall for stereo, the search range is just a 1D line. So it's we don't need much computation. But recall for flow, the search range is all the possible pixels in the second frame. And there are some recent work, including FlowNet, who are trying to build a full Kautz volume. But the computation is a bottleneck. Another problem is the scale. For example, if we crop this small patch here, we can see there is a strong response along this vertical line. So this local ambiguity is also called the aperture problem in optical flow. So to resolve this issue, we need to crop a much larger size to well-localize the motion. However, we also need to crop the size very carefully so that the foreground car will not be confused with the background. So how can we deal with these two issues? And here is our proposed solution. The first is we are going to construct the Kautz volume at multi-resolution using pyramids. And so it seems like we are going to increase the computational cost. And so this is our second idea. Always use a small search range. But can we use a small search range to deal with large motion? So next, I'm going to show how. So this is our algorithm. First, given the two input image, we construct a feature pyramid. Suppose this is the typical input size, the width, height, and trend number. This will be the spatial size and the trend number for the feature pyramid. As we can see, at the smallest level, the size is very small, it's 16 by 8. But at this level, every pixel actually has a very large receptor field. And now I'm going to show how to construct the Kautz volume using the features. So the idea of using correlation was first introduced by Florence. So I will use these two features to explain the idea. So suppose we pick our pixel in the first frame. This is its feature here. And then we pick another pixel in the second image. We compute the correlation. This gives us a number, shows how similar these two features are to each other. And then we search over the second image. And vectorize the result. This gives us the cost for this particular pixel in the first frame. And then we sweep over all the pixels in the first image. This gives us the whole Kautz volume. And because the spatial size of the feature here is very small, we can use a very small search range, which is computationally efficient. And next, we are going to concatenate the Kautz volume with features of the first pyramid and give it to the CNN to map to the optical flow. And given the optic flow estimation at the current level, we can upsample and rescale it to the next level. Now the question is, how can we going to use this upsampled flow at the next level? So here comes another great principle from the literature called warping. I will use the image to explain the basic idea. So given the upsampled flow, we can warp the second image toward the first. This gives us the warped image. And the motion between the first image and the warped image is very small. So that means we can use a very small search range to construct the Kautz volume. Here is an example. You can see the motion between the first image and the second image is much larger than the motion between the first image and the warped image. And now I'm going to use the idea of warping into our network. So given the upsampled feature, the upsampled flow, I will use the flow to warp the feature of the second image. Let's give us the warped feature. And then I will use the warped feature and the feature of the first image to construct the Kautz volume. Because warping has already compensated for the large motion, we can use the small search range. And then we will concatenate the upsampled flow, the Kautz volume, and the feature of the first image, give it to CNN to map to the refined optical flow. And then we upsample and rescale the flow, get to the next level, and apply the same processing. So that's how our algorithm works. And now I'm going to have a comparison with a prior work who also used the same principle, some of the principles, but in different way. For example, Spatial-Aware built an image pyramid. And Florence 2 used a 3-level feature pyramid in the first module of its big network, that's the Florence C. But for PWC-Net, it used a much deeper 6-level feature pyramid. And second, warping, Spatial-Aware and Florence 2 apply warping to the image. But PWC-Net warps the features so that the information can better propagate through the whole feature pyramid. And finally, Spatial-Aware does not use Kautz volume. And Florence 2 uses it just once, but with a very large search range in the first module. But for PWC-Net, it constructs Kautz volume at every level of processing. And because of warping, we can use a very small search range. So now I'm going to check the effectiveness of the 3 principles: pyramid, warping, and Kautz volume. And for this study, we train all the models using the flying chairs and test it on the final pass of the Singtel training dataset. This is the endpoint error for PWC-Net using the 3 principles. Like the lower the better. And if we replace the feature pyramid with the image pyramid and keep everything the same, we can see there's about 30% drop in performance, showing the benefit of learning the features. And if we remove the warping operation from the network, we just use the features of first image and second image to build the cost volume. There's about 20% drop in performance. And finally, if we remove the cost volume from the pipeline, we directly feed the features of 2 images to the CNN, there's again another 15% drop in performance. So all shows the benefit of using the 3 principles. And so by making very frequent use of these principles, we can obtain a very compact size model, but also perform very competitively against the state of the art. This is the Singtel final pass table at the time of submission. PWC-Net was top ranked. And we archived our paper in last September. And 2 months later, we make the CVPR submission. And there was about a 10% improvement in performance. And I received quite a few inquiries about what's the difference, because the network is exactly the same. So something we found critical is, for this with very limited training data augmentation plays a very important key. For example, when we fine-tuning on Singtel, we do not add Gaussian noise because the Singtel data are already very clean. And also, adding horizontal flipping can effectively reduce the overfitting issue. And this is the result of the recent robust vision challenge in the optical flow track. The requirement is to use the same parameter across all the 4 benchmarks, like Middlebury, KT, Singtel, and HD1K. PWC-Net is a winning entry. So to sum up, I have introduced a very compact but effective model using 3 principles: pyramid of features, warping the features, and construct a cost volume with very small search range. And finally, the cafe and PyTorch code are available at this GitHub link. And thank you for your attention.
So if anybody has any questions, please come up to the microphone. All right, we have one back there.
Hello. Thank you for the talk.
Yeah.
There is another paper in this conference called TV-Net, which basically converts the TV-L1 algorithm into a neural network. They also reported better speed and better results than FlowNet 2. Of course, you did not compare with that one because in the same conference, just wonder. So have you noticed that one, or if you compare these two, what would be the difference? TV-Net and your network.
So actually, I haven't read the paper, so maybe can you briefly explain the idea again? I think it's a good idea to build the TV-L1 player into the network.
Yeah, the idea is basically TV-L1, you have an optimization procedure step by step. Every step you compute the gradients, compute divergence, and you do the thresholding. All these operations can be implemented by some filters.
Right.
So therefore, you can convert it into a neural network.
Yeah, I think I cannot say about the performance, but I think these two work share the same spirit. That's to build the domain knowledge into the network. So I'm very happy to see that other people have the same idea. Yeah.
Okay.
Thank you.
Okay, let's thank our speaker one more time.
Our next speaker is Zhiyang Fan, and he's going to talk to us about deep intrinsic image decomposition. We need a different angle. Is there any technical help? Oh, yes. Could you?
Okay, we're having some technical difficulties with the second oral presentation, so we're going to skip that for now, and we're going to move on to the third oral presentation. So our presenter for this is going to be Florence Yellin, talking about multi-cell detection and classification using generative convolutional model.
Hi, my name is Flora Yellin. Today I'm going to be talking about multi-cell detection and classification using a generative convolutional model. This work is funded by My Diagnostics. So how many of you are familiar with this device and have one of these at home? Please raise your hands. So this thermometer is one of the most important diagnostic tools used today, and almost everybody here has access to one of these at home. A second very important diagnostic tool is the blood test. Now, how many people have a hematology analyzer at home? So the hematology analyzer provides the complete blood count, which is the most commonly requested blood work by doctors today, and nobody here has access to one of these at home. Our goal is to make blood work as accessible as the thermometer. The way we envision doing this is by using computer vision for blood cell detection, counting, and classification. We'd like to take an image, such as the image on the right of white blood cells, and be able to count the total number of cells in the image and to classify what percentage of the cells belong to each of the three main subclasses of white blood cells: granulocytes, lymphocytes, and monocytes. However, we don't have access to high-resolution microscopy images such as these. Instead, we work with reconstructed lens-free images that look like this. So here's another image of blood cells that was produced using the standard reconstruction, and you can see that the blood cells are the small dark objects and that there's a lot of background distortions. Instead, we use the sparse phase recovery reconstruction that we introduced recently, which produces much clearer images by doing phase recovery. However, despite the better reconstruction method, we're still plagued by low-resolution images compared to conventional microscopy. So why use lens-free images at all? Lens-free imaging allows for a very compact system that's also low cost. Furthermore, if we zoom out on the image of a single cell, you can see that we have very large field of view images compared to conventional microscopy at the same magnification. These advantages are crucial if we want to make blood work accessible. Our goal is to take a lens-free image, such as one of these, of white blood cells, and to be able to detect, count, and classify all of the cells in the image. How might we go about doing this? One possible approach is to do thresholding to detect the cells, to then extract the cell patches, and to use a classifier like a CNN to obtain the class labels. However, a disadvantage of this approach is that it doesn't take into account prior distributions for blood cell populations. For example, we know that a typical patient has 8% monocytes, 24% granulocytes, and the rest of their blood cells, 24% lymphocytes, and the rest of their blood cells granulocytes. So it doesn't really make sense to independently detect and classify every cell in the image because we don't have an obvious way to incorporate the prior distribution for blood cell populations. Another challenge that we're faced with is that we only have coarse grain labels for our images. For each image, we know the total number of cells in the image and what percentage of them belong to the granulocyte, lymphocyte, and monocyte classes, but we don't have bounding box annotations. Even if we were to use a method like thresholding to produce bounding boxes, we would still be missing the labels. In this paper, we propose a method to detect, count, and classify cell populations in lens-free images. The idea is shown in the figure. We look at the correlation of every pixel in the image with class templates, and regions with a high correlation will likely contain cells of that class. However, we also incorporate the class proportions, the prior distributions, and the way we do this is by introducing a generative probabilistic model for multi-object detection and classification. We also explain how to do weakly supervised learning without per-object bounding boxes. Finally, we propose an efficient inference method to detect, count, and classify populations that have hundreds to thousands of cells per image. So I'm first going to go over the generative model. The first piece of the model incorporates the cell population priors. We first draw the number of cells n from a Poisson distribution, and we then sample the cell class S from a categorical distribution. The second part of the model is a convolutional model for multi-class objects. Given the cell class of each cell, we associate with each cell a template, Ki, which is drawn from a uniform distribution. For simplicity, let's assume that the templates look like these shapes. So we have square templates, circles, and stars. We sample the cell location, xi, yi, from a uniform distribution, and the detection strength, alpha I, from an exponential distribution. The idea of the detection strength is that it indicates how brightly each object appears in the image. So for high values of alpha I, the cell will appear brightly, and for low values, it will appear faded in the image. Finally, we assume a multivariate Gaussian distribution for an image, given the cell templates, detection strength, cell locations, and the total number of cells in the image. The idea of this is of the convolutional model is depicted in the cartoon here. An image that contains circles, stars, and squares can be decomposed into 3 separate images, each one containing the convolution of a delta function at the location of the shape templates with the shape template itself. So now that we have the model, we can write down the joint distribution, which has 2 pieces. One piece just incorporates the priors on the cell populations, and the second piece is a convolutional model for images. Each of these parts have parameters that we need to learn. To do parameter learning, recall that we don't have the typical bounding box annotations. So instead, we employ 2 separate data sets to train the different model parameters. The first data set will be used to train the image parameters, such as the cell templates. And the second data set will be used to train the cell population parameters, for example, the mean number of cells in an image. So the first data set that we use is data that comes from reconstructed lens-free images of purified blood samples. What this means is that an experimental procedure has been done to isolate cells belonging to a single subclass to obtain something called purified blood. So we now know the class of the cells in the image, and we can use approximate expectation maximization to train the image parameters. For example, we can use a granulocyte image to learn the granulocyte templates. But it doesn't make sense to use this data to learn the population parameters. For example, if we want to know the probability that a cell in an image is a granulocyte, it doesn't make sense to learn this from a sample that has been experimentally modified to contain 100% granulocytes. Instead, we use a second data set, which comes from the complete blood count results from 300,000 patients. This data set does not contain any images. It only contains the number of cells per sample and what percentage of them belong to each of the cell classes. So without having any images, we can then train the population parameters, such as the mean number of cells in an image, or learn what the probability that a cell belongs to the granulocyte class is. Finally, we'd like to do inference. So given a new image, we'd like to jointly figure out what the cell templates are, the cell locations, the detection strengths, and the number of cells in the image. And we do this by maximizing the log likelihood jointly for all these variables. We use a greedy method, which is similar to matching pursuit. So rather than detecting all n cells in the image at once, we'll use n iterations to detect and classify a single cell at a time. The idea is that we define a residual image, which is initially equal to the input image. At each iteration, we detect and classify a cell and remove it from the residual. And this procedure continues until all of the cells have been removed and all that's left is the background noise. And notice while this runs that the larger cells are being detected before the smaller cells. The idea is shown in the equation above. So if you look at the correlation of the residual image with the templates, the area with the largest response will probably contain the next cell. However, there's also a second term which takes into account the cell population priors. And finally, just note that this method is efficient. It involves only local updates at each iteration, so we can efficiently detect and classify hundreds or thousands of cells in an image. In order to count the number of cells, we have to terminate this procedure at the correct time, because the number of iterations is equal to the number of cells detected. We derive a stopping condition, so we stop detecting cells in an image when the strength of detection squared is below a certain threshold. Now recall that we were detecting the larger cells before the smaller cells. So if the threshold is slightly incorrect, this won't have huge implications in terms of the counting, but it could potentially have big implications for classifications. We might overcount the cells belonging to the large class while undercounting cells belonging to the smaller class. So a key advantage of our method is that our stopping condition is class dependent. So even if we first detect the large cells before the smaller cells, we won't terminate until we've also reached the threshold for the smaller cells. Finally, I'm going to go over the results. We have reconstructed lens-free images of white blood cells containing granulocytes, lymphocytes, and monocytes mixed together. And we'd like to be able to estimate the white blood cell populations and predict the class proportions. And we're going to compare our results to the Hematology Analyzer for ground truth. Now, it's important to make sure that our method can perform well not only near the distribution means, but also on the tails of the distributions. And for this reason, we've obtained blood samples that come from both normal donors that tend to lie near the means of the distributions and abnormal donors that tend to lie on the distribution's tails. You can see, for example, in the leftmost figure, it shows the histogram with the number of blood cells in the 300,000 patient samples from the training database. And the region highlighted in gray indicates the range that our samples cover for testing. First, I'm showing the results for cell counting. On the x-axis is the ground truth, and on the y-axis is the predictions for our method, thresholding, and convolutional sparse coding. And while our method slightly outperforms the other two, all of the methods are shown here are able to produce relatively good counts. The real advantage of our method is evident when you look at the class proportion results. Now I'm showing on the x-axis the ground truth percentage, and on the y-axis the predicted percentage of granulocytes, lymphocytes, and monocytes. So perfect prediction would mean that all of the points lie exactly on the black diagonal. It's clear that our method outperforms the CNN and convolutional sparse coding, and this is true for both the normal donors shown in X's and the abnormal donors that are shown in O's. We can quantify this by looking at the mean absolute error compared to the Hematology Analyzer. And in all cases, our method outperforms the CNN and convolutional sparse coding. For example, if you look at the results for just normal donors, the mean absolute error for our method is less than half that from the CNN or CSC. In conclusion, we've shown that we've introduced a generative model. We've shown that we can do inference for detection, counting, and classification. We've described how to do parameter learning with our unique data. And we've shown that our method outperforms other methods in terms of predicting the cell population counts and the class proportions. This method can potentially be expanded also to other images that contain multiple object instances. Thank you for your attention.
So we have time for a few questions. Give you guys a few seconds to build up the courage. No? Okay. I guess, it's exciting to me to see something beating a CNN on a particular important application. So I'm curious if you could talk a little bit more about why you think your approach is outperforming the CNN on this task.
Yeah, so that's a good question. The images are very low resolution, so they're very difficult to classify correctly. And we don't have tremendous amounts of training data like you do in some application, and we don't have normal annotations also. So in this case, it makes more sense to kind of constrain our answers to only solutions that make sense, which is what we're doing by using a model.
Okay. And if you were to get more training data, do you have a sense for how much training data you would need to get for a CNN to start approaching the performance level?
I would imagine that if you have enough training data, you could kind of teach the CNN what the population prior term should be. But you'd have to have a lot of both normal and abnormal blood samples, which are hard to come by. So a lot more than what we have currently.
Okay, let's thank our speaker one more time.
And I think now we're ready for Qingnan and intrinsic image decomposition.
Today I'm happy to be here to introduce our work, revisiting deep intrinsic image decompositions. I'm Qingnan fan from Shandong University. This is joint work with Jiaolong Yang, Ganghua, Baoquan, Chen, and David Wipf. The goal of intrinsic image decompositions is to separate an image into two layers, an albedo image which demonstrates the intrinsic color of the objects, and a shading image which indicates the lighting condition in the environment. These two images can be per pixel multiplied to form the original image in the ideal diffuse scene. By solving such a problem, we can implement some interesting visual effects. For example, resurfacing. As shown here, the car border is colorized with another texture to generate a new scene without influencing the lightings. On the other hand, we can also insert some new objects in the scene by rendering the 3D objects with the estimated illumination in the image and placing them in the target position, just like the blanket on the bed. Estimating the decomposition is a fundamentally ill-posed problem, as there exist infinitely many feasible solutions to the above equation. To tackle such a problem, prior information is always leveraged to constrain the space of feasible solutions. However, given access to ground truth intrinsic image datasets, deep convolutional neural networks provide a data-driven candidate solution with fewer potentially heuristic or handcrafted assumptions. But the challenge of applying CNNs is lack of a variety of ground truth data. Let's look at the major datasets for this task. The most widely used dataset is MIT intrinsic dataset. Its images are obtained by capturing the input diffuse image, shading image, which are further employed to calculate the reflectance image. However, capturing such a dataset is labor-intensive and requires highly controlled scene. Therefore, this dataset is limited to images of single spatialized objects, which lacks diversity and scene-level realism. Another kind of benchmark known as MPI Centil dataset is generated while rendering an open-source animation movie. The rendered images often lack realism, and the traditional deep networks trained on these data may perform poorly on more natural examples. A more recent IIW dataset was created from real-world photos. Although dense ground truth decompositions are not available, pairwise reflectance comparisons have been labeled via AMT for a sparse collection of points in each image. Due to lack of ground truth dense image labels, it becomes difficult to employ a deep network to directly generate the high-quality intrinsic images. The previous intrinsic image works are mostly specifically tailored for a particular data source. To overcome such limitations, we introduced our proposed framework that can be shared by different data sources using flexible supervision. Furthermore, we obtain better performance on real images by jointly leveraging multiple data sources. For the IIW data, where labeling is restricted to sparse pairwise comparisons of relative reflectance, we adopt the common assumption that the scene lighting is chromatic that is commonly done for this data source. Therefore, given an input image, we only require to produce a scalar albedo intensity for every image pixel. Then this albedo intensity can be expanded to the full albedo across all 3 color channels using this differentiable transform. The employed direct intrinsic network is a fully convolutional neural network, which is equipped with residual blocks and dilated convolutions. The initial cost estimation of this reflectance is already able to demonstrate excellent numerical performance. However, as the supervised label is only located on a sparse set of points in the image, the direct estimation of intrinsic images does not always preserve the flattening effects exhibited by natural reflectance images, as can be seen in the amplified region. To eliminate such artifacts, we apply a filtering pipeline described as follows. At first, we compute an input edge map as the absolute difference between each point and its surroundings for the input image. We feed the computed input edge map along with the input image to a guidance network, which shares a similar network structure as the direct intrinsic network, to predict a sparse edge map, which serves as the guidance map for the later filtering purpose. Given the ground truth albedo image, the supervised guidance map can be directly computed from it. But for the IIW data, which lack such dense image labels, we calculate the guidance map from the edge-preserving smoothing results generated by this paper, which represents a highly piecewise constant images as required by the albedo image. Afterwards, guided by the learned edge map, the albedo image is processed by the chip domain filter to generate a realistically flattened albedo image. The domain filter admits an efficient implementation via separable 1D filtering layers. For input 1D signal X, the filtered output signal Y can be defined on the transformed domain of guidance map using the mentioned equation. Such a separable 1D recursive filtering layer is applied across rows and columns in an image, which means performing a horizontal pass along each image row and a vertical pass along each image column. along 4 different directions in an iterative manner. Note that the domain filters are parameter-free and support pack propagation. As can be seen in the amplified regions, the final albedo image looks much smoother than the one without being filtered. The corresponding shading image can then be directly calculated based on the input image and the predicted albedo image. Regarding the datasets such as MPI, Centil, or MIT datasets with densely labeled ground truth, chromatic lighting assumptions do not always hold. It is more suitable to replace the albedo prediction module by separately outputting full albedo and shading layers. Therefore, the basic network structure described above is split into 2 branches from within the intermediate direct intrinsic networks, one for albedo and another for shading, where the latter of which does not need to be calculated later. As a generic network is developed to learn from multiple types of data sources, we propose a flexible supervised loss layer that can be customized to the distinct form of available ground truth labels. We begin with pairwise relative reflectance judgments as found in the IIW dataset. Given a predicted albedo image, a classification of reflectance pairs can be calculated with the above equation. Whereas ground truth pairwise comparisons is labeled by AMT workers as shown in the IIW dataset. As no dense ground truth labels are available, IIW introduced the WHDR error metric, short for weighted human disagreement rate, to measure the percent of human judgment that an algorithm disagrees with. This metric is naturally converted to a form of modified hinge loss that can be conceptually evaluated at every possible pair of points across a dense trainable albedo image estimate. Thus, the albedo image output from the entire proposed framework can then be supervised. Beyond this supervision at the output of our pipeline, we also provide intermediate supervision, both to the grid scale albedo intensity and the setting element. When dense ground truth intrinsic images are available in the MIT and MPI Centil datasets, we directly utilize the mean squared error as a supervision layer for all outputs. For the outputs of the directly intrinsic network, we supervise both the albedo and the shading. Additionally, to help preserve the details of intrinsic images, the image gradients in the X and Y directions are also supervised here. Now we present both numerical and visual results on the aforementioned benchmarks. This figure displays runtime comparisons plotted against the WHDR performance metric across a wide array of competing methods. Our full pipeline achieves the best numerical performance, which is significantly better than the second best one. While obtaining the highest accuracy score, our system is still much faster than most others. Here we demonstrate some representative visual examples, which illustrates dense extrapolated decompositions across the entire images. Where one approach shows some abrupt color transitions along the front and side of the couch that at least by visual inception presumably should have the similar albedo. Note our method achieves nearly flattened albedo images, which however contains a spurious noise in previous methods. Similar phenomenon can also be observed in this example. We also evaluate our algorithm on the MPI Centil dataset that facilitates scene-level quantitative comparisons with densely labeled training data. As shown in this table, our model achieves the best results for all the columns on the MPI Centil data. Here is a group of qualitative results. It can be seen that our framework produces much sharper and high-quality results, and visually very close to the ground truth shown in the last row. Similar visual results can also be observed in the MIT dataset. Our predicted images are also sharper and more accurate than the other deep networks. Finally, we found that simultaneously training on multiple datasets is a natural consideration given the generic modular nature of our pipeline. To briefly examine this hypothesis, we jointly trained our model on both IIW and MPI datasets with shared network parameters. Experimentally, we obtained a mean WHDR that is better than all previous methods, but not quite as good as our previous results when trained solely on IIW. This is not surprising, since the dense synthesized MPI data is unlikely to closely reflect real-world images and IAW pairwise comparisons. But crucially, MPI data can still provide useful regularization of real-world image structures, even though this benefit may occur away from sparsely labeled points, and hence contributes no quantitatively measurable value. This figure supports this conclusion, where our jointly trained model is applied to 3 real-world images. Here we observe that complementary supervision does, in effect, enhance the qualitative performance in the new testing environments. And our joint model smooths various artifacts. Detailed difference can be observed in these magnified regions. To summarize, in this paper, we propose the first deep architecture capable of achieving state-of-the-art results when applied to each of the major intrinsic benchmarks. Moreover, our framework is also the first trainable end-to-end system on the most challenging IIW benchmark. We achieved significant improvement over both unseen indoor and outdoor real images, while joint training multiple data sources. Compared to previous approaches, our method only requires a minimal computational footprint at test time. So one last thing, I'm gonna graduate in the summer next year, so I'm looking for potential postdocs and jobs. So if anyone is interested into my research, you can feel free to contact me. That's it, thank you.
Are there any questions? Please line up on the mic. So let me start with a question. So you showed some nice architecture that had to impose nice smoothness priors and other types of priors to regularize your predictions.
Yep.
Given how many gun papers we've seen this conference, I'm wondering why didn't you put a gun also there to impose such priors, for example?
Yeah, that's a pretty good question. Actually, previously we also think using because we think again it's more suitable for kind of domain transform tasks from given the edge map, you predict some images and that have contents based on the edge map you already have. But for this specific task, I think we already have the ground truth labels. So again, it's kind of like unsupervised learning, but here we already have the ground truth labels, so it can just directly learn the thing we want. Yeah, I think.
Okay. And I was wondering, based on the results, it showed that this tiny MIT dataset is valuable for, when it's jointly trained with a very large Cornell dataset, right?
Yeah.
So
actually, when joint training the multiple data source, we didn't kind of incorporate the MIT because the MIT is kind of only have maybe hundreds of images, and it's kind of far from the other two. And the other two have like 5,000, and another have maybe 2,000 images. So
I see. So diversity is very important for
Yeah, it's very
transferability of the
important.
features. Okay.
yeah,
great.
right.
All right. Let's thank the speaker again.
Okay, thank you.
Now we're going to start with the spotlights. Is this the first? Please, each time the subsequent spotlight presenter to wait here in the chair. We're missing some spotlight presenters. Could you please come to the front? Okay, great. I think we're ready to start.
Hello everyone, my name is Chong and I'm from Dalian University of Technology. The title of the reported paper is Learning Spatial-Aware Regressions for Visual Tracking. Firstly, about the motivation of the proposed method. The kernelized regression model has limited model parameters, and this limits the model representation ability. On the contrary, the CNN model has tens of thousands of parameters and may be susceptible to the overfitting problem. Okay. So I will restart. sorry, I will restart. Hello everyone, my name is Chong and I'm from Dalian University of Technology. The title of the reported paper is Learning Spatial-Aware Regressions for Visual Tracking. Firstly, about the motivation of the proposed method. The current regression method has limited model parameters, and this may limit the model representation ability. On the contrary, the CNN model has tens of thousands of parameters and are susceptible to the overfitting problem. Our method jointly considers the KR and CNN models. The KR model focuses on holistic target, and the CNN model focuses on small and localized region. The first row of this slide shows the original regression method. By introducing the representative theorem, we obtain the correct regression model. The showing process for both the alpha and beta this work incorporates the cross-path similarity kernel into the KR, and this leads to the optimization problem in the third row. In this work, we compute the response for the traditional solver for the optimization problem in the should be the ADMM method, which first fixes alpha and solve beta, and then fixes beta and solve alpha. The solving process for both alpha and beta are very time-consuming, as it is shown in the slides. In this work, different from the original method, we try to compute the response from the KR model in 3 steps, which can be reformulated as a neural network. The 3 steps are named as A and B and C respectively. The reformulated neural network is presented in this slide. In the neural network, altogether there are 3 modules, which are respectively named as module A, B, and C. We provide the forward and backward operation for each module, which ensure the end-to-end training of the proposed network. In this slide, we present the learned reliability weight for the proposed network. In this experiment, we divide the target object into 9 patches, and we saw the learned weights for each patch and the cross-patch similarity. In the first example, our model can accurately detect the 5th and 9th patches are more reliable than others. We also provide a neural network with spatially regularized filter kernels. Compared to the previous methods, our method incorporates the 2-stage training strategy and distance transform pooling layer. It can also better handle rotations. This slide shows how we compute the spatial regularized filter kernels. Let FC denotes the filter kernel with associated with the channel C of the output feature map OC. Then OC can be computed by the following formula. By this means, we force the response map corresponds to different filter kernels to force on different target regions, which can also help avoid the overfitting problem. The experimental results in this slide shows that by introducing spatially regularized filter kernel, the neural network focuses on more target regions, by which means increasing model diversity. We use the response from the KR and CNN models to obtain the final tracking results. It's easily to be seen that the improved tracking performance can be achieved via the combination of the 2 neural networks. As to the experimental section, we conduct dense experiments on both OTB and VLT datasets. Our tracker has impressive tracking results on both of the reported datasets. It's noted that the proposed tracker has the best performance on the VLT 2017 public dataset. Okay, this slide shows the results on the VLT challenge dataset. And we can see that our tracker also has the best results on almost all the attributes categorized by the tracking challenge. Okay, that's all. Thank you.
Hello, everyone. I'm Bo from SAMSTEM. So in this paper, we propose a network that unifies Simon's network and the region proposal network. Our motivation is that most trackers do not have a regression network, which limits their ability to predict the shape during deformation scale variance. So they need to perform multi-scale tests to obtain the best scale of the target. Another motivation is that most trackers cannot balance the accuracy and speed. Trackers with high performance can hardly track with real-time speed. Based on these motivations, we introduced regions proposal network into our tracking framework. And our main contributions can be summarized as follows. Firstly, we propose the Simon's region proposal network, which is end-to-end trained offline with large-scale image pairs. And secondly, during online tracking, The proposed network is formulated as a local one-shot detection task, which can refine the proposal to discard the most expensive multi-scale test. And in experiments, Samsung RPN achieved leading performance in recent VOT challenges with the speed of 160 FPS, which shows advantages in both accuracy and efficiency. And here is the main framework of Simon's RPN. And it consists of Simon's subnetwork for feature extraction and region proposal network for proposal generation. And our network is trained end-to-end with large scale of image pairs extracted from both VID and YouTube bounding boxes. YouTube bounding boxes has 50 times more videos than VID, which is able to train our network much better. Okay. During the test phase, the task is formulated into a one-shot detection task. The template branch predicts the weight for the kernel of RPN only in the first frame. Then the template is pruned, and only the detection branch is retained. And in VOT 2015, our tracker can obtain the top performance with high speed. This slide shows our performance in VOT 2016. Compared with the champion CCOT, our tracker is better than it, while performing 500 times faster than it. In VOT 2017 real-time challenge, our tracker is better than the best tracker on board with 3 points. And this slide shows our tracker is better when more data is imported into training. And this figure also illustrates our tracker can achieve better performance when more data is available. And here is the visual result of our tracker compared with CCOT and Simon's FC. Thanks to the region proposal network, Simon's RPN is able to predict the shape of the target more precisely. Okay, that's all. Thank you.
Hi, my name is Kevin Loy. So I'm here to bring you another lightweight network for optical flow estimation. So our method is called LightFlowNet. It's inspired by the success of FlowNet 2. Performance-wise, LightFlowNet is on par or outperforms FlowNet 2 on real-world data. Flow fields from LightFlowNet are sharp. It's rather rare to observe artifacts. The key difference is that LightFlowNet is a very compact network. It has about 5 million parameters. This is over 30 times smaller than in the model size and 1.36 times faster than FlowNet 2. Here are some key differences between FlowNet 2 and our LightFlowNet. First, we design a specialized architecture that corresponds to data fidelity and regularization terms. Second, we address the problem of large flow displacements by feature warping instead of image warping. Third, we introduce a cascaded flow inference for more accurate flow field estimation. Fourth, we introduce a feature-driven local convolution for flow regularization. So all these components contribute to the smaller model size and also faster speed in LightFlowNet. So LightFlowNet is composed of two subnetworks. So NetC, the one on the left, acts as a feature extractor, and NetE, the one on the right, is specialized for optical flow estimation. Given an image pair, NetC transforms each image into a pyramid of multi-scale high-dimensional features, and NetE is designed to infer multi-scale flow fields from the features. So this design uses a lighter network compared to FlowNet 2. And during the inference, cascaded flow inference is first performed by using the features from the feature pyramid, And then flow regularization is then performed to address weak flow boundaries and undesired artifacts. So we repeat this inference and regularization steps until the desired spatial resolution is obtained. Different from FlowNet 2, we perform cascaded flow to gradually refine the flow estimate at each level. This is achieved by 2 units. The first unit in the cascaded flow inference is a descriptor matching unit. What it does is to construct a cost volume to capture pixel-to-pixel correlation between the 2 frames features. We then filter the cost volume to get a residual flow, which will be added to the previous flow field estimate to form a complete flow. The flow is then passed to a second unit, which is called a sub-pixel refinement unit. The main objective of this step is to refine the flow field of the previous unit. It will produce a residual flow, which is then combined with the flow field of previous unit to generate the complete flow. So I will give more details during the poster session. So a very unique component in our network is flow regularization. This is achieved through feature-driven local convolution, which is adaptively constructed using pyramidal features, flow estimate, and occlusion probability map. To improve the computational efficiency, each local filter or flow patch is packed into a 3D tensor. And once the 3D tensors are ready, then local convolution can be efficiently performed by a tensor dot product. So the next figure, this figure summarizes the effectiveness of different components in LightFlowNet. Feature warping addresses the problem of large flow displacements, and cascaded inference provides further performance to generate sharper and more detailed flows, and regularization helps to elevate those weight flow boundaries. So this is a short clip to showcase the performance of LightFlowNet. So the codes are already available. So welcome to the poster to discuss further. Thank you.
So in the following, I will illustrate our work on Wipf tracking. The title is Vital, Wipf tracking via adversarial learning. The authors are mainly from the Ming-Hsuan AI Lab, the University of Adelaide, Harbin Institute of Technology, and the University of California at Merced. In Wipf tracking, we aim to locate single target object in the videos. Given one ground truth object annotation in the first frame, we develop algorithms to track the target object in the remaining frames. As there is no prior knowledge of the target object except for the first frame annotation, it is quite challenging to accurately track the object, especially when it contains significant appearance variations. Examples include in-plane and out-of-plane rotation, illumination variance, occlusion, and deformation. The state-of-the-art tracking by detection framework typically consists of 2 steps to localize target object. In the first step, we draw multiple samples near the target region of the previous frame and classify each sample as either the target or the background. The online training process of the classifier is based on each input sequence. In the initial frame, multiple samples are collected and labeled based on their overlapping extent with the ground truth annotation. They use these samples to train a binary classifier which differentiates the target and the background in the next few frames. In practice, we find that the positive samples are all around the target object, which are highly overlapped. These samples are not able to capture the rich appearance variations over time. Meanwhile, the extreme background, foreground, and background class imbalance negatively affects training the classifiers. So in this work, we take advantage of the recent progress in adversarial learning to augment positive samples to facilitate classifier training. Meanwhile, we propose a high-order cost-sensitive loss to decrease the effect of easy negative samples. So we present our framework here. It consists of feature extractor, adversarial feature generator, and a binary discriminator. The generative network augments positive samples by generating weight masks randomly applied to the features, where each mask represents a specific type of appearance variation. Through adversarial learning, our network can identify the mask that maintains the most robust features of target appearance in the temporal domain. The learned mask is able to decrease the contributions of discriminative features, which tends to overfit the classifier in a single frame. In other words, adversarial learning helps our tracker to exploit robust features over the temporal span, rather than overfitting to discriminative features in a single frame. So we evaluate the proposed tracker vital on the visual tracking benchmarks, including OTB and VOT, using standard metrics. The distance precision and overlap success rates shown in these figures here indicate that the proposed tracker performed favorably against state-of-the-art approaches. So in sum, we propose a tracking by detection framework with adversarial learning scheme to adaptively enrich the target feature representations in the CNN feature space. It reduces the overfitting problem of the classifier when it handles target appearance variations over the whole temporal sequences. Meanwhile, we propose a cost-sensitive loss to reduce the effect of easy negative samples for overcoming the class imbalance problem. We adopt both strategies in the training step to generalize a temporally robust classifier which improves the baseline while achieving favorable performance on standard benchmarks. The details are presented in our poster. You are welcome to our Counter G19 for further discussions. Thanks for your attention.
Good afternoon, everyone. Today I'm going to introduce super slow-mo, high-quality estimation of multiple intermediate frames for video interpolation. This is joint work with my PhD advisor and NVIDIA researchers. Given an input video, our approach is able to generate arbitrarily higher frame rate variance, for example, 8 times higher or even higher, like 36 times. Here's another example. Unlike most of existing approaches focusing on generating a single intermediate frame, our approach is able to do multi-frame variable length video interpolation. So how do we do this? Given input images, we like to insert an intermediate frame at time step t. For this purpose, for each pixel at time step t, we predict its bidirectional correspondences to both input images in terms of optical flow. We then blend corresponding pixel values of both input images to synthesize the intermediate frame. However, not all pixels can, at time step t, can find their correspondences in input images due to occlusion. To this end, we predict visibility weights of both input images to control their contributions to intermediate frame synthesis to deal with occlusion. So bearing these ideas in mind, we have network design of our super slow-mo consisting of 2 major parts. In the first part, given 2 input images, we have a neural network to predict bidirectional optical flow between them. In the second part, at each time step t, we first get an approximation of bidirectional intermediate optical flow. We then have another separate neural network to get refined intermediate optical flow as well as pixel-wise visibility maps, which are finally used to synthesize an intermediate frame. Since none of the network's parameters is dependent on time step t, our approach is able to do multi-frame variable length video interpolation, generating as many intermediate frames as we want, using the same network without any modification. Here are some illustrations of intermediate results. Given input images, we predict intermediate optical flow at time step t, which are used to warp both input images. We also predict pixel-wise visibility maps of input images, which are used to blend warped input images to synthesize an intermediate frame. We can see in this example, visibility maps help generate better interpolation results. Especially around motion boundaries, the athlete's arms, there are less artifacts by using visibility maps. Now I'd like to show some quantitative results where 31 intermediate frames are generated. The higher curve, the better it is. We can see our approach consistently generates better video interpolation results, outperforming all other approaches at each time step. Our approach is also able to train a neural network to compute optical flow in a self-supervised manner without using any ground truth annotations. Here are some visual results. We can see our approach generates good optical flow between input images. To conclude, there are 2 key messages to take away. First, our approach is able to do multi-frame variable length video interpolation, generating as many intermediate frames as we want. Second, we show video interpolation can serve as a surrogate task for optical flow learning without using ground truth annotations. Welcome to our poster G21 for more technical details and more results. There is also a live demo at NVIDIA's booth that you can play with. Thank you.
Good afternoon, CVPR. My name is Tom Rinia, and this is joint work with Kees Snoek and Arnold Smulders from the CUVA Deep Vision Lab at the University of Amsterdam. This intro video illustrates the presence of visual repetition in the world around us. As you have seen, visual repetition is ubiquitous in the world around us, and it appears in many forms. In this work, we consider the task of estimating repetition in video under realistic circumstances. First, we revisit the theory of periodic motion. Starting from the 3D motion field, we tied to a moving object, we use first-order differential analysis to arrive at 9 fundamental cases of periodic motion. Our method requires no learning, but rather builds on the theoretical insights. And different from existing work, our method is able to handle non-stationary repetitions, such as accelerations and non-static appearance. Finally, we propose a new video dataset and show that our method outperforms existing work on the task of repetition counting. The starting point for our theory is the 3D motion field. We follow a first-order differential approach using the operators divergence, gradient, and curl to arrive at the categorization of periodic motion types. Specifically, the spatial differential operators divergence and curl are used to derive 3 fundamental motion types: translation, rotation, and expansion. And in a similar fashion, 3 periodic motion continuities emerge from the temporal dynamics, being constant, intermittent, and oscillating motion. Together, these motion types and motion continuities organize in a table of 9 fundamental cases of periodicity. Here we present the abstractions of their flow field and the corresponding real-world examples. For the intermittent and oscillating case, the periodicity is intrinsic in the temporal dynamics, whereas for constant motion to appear as periodic, a repetitive appearance is required. For 2D video, the viewpoint location relative to the moving object needs to be considered. We show that 2 viewpoint extremes, being side and frontal, span the continuous range. On top of the 9 cases in 3D, this produces 18 cases of repetitive appearance in 2D. In practice, the appearance may be somewhere in between those viewpoint extremes. Our method for repetition estimation uses motion localization and filtering. We first segment the foreground motion using an off-the-shelf method. Then we represent the salient moving object by 6 first-order motion maps, including the divergence, gradient, and curl, of which only 4 out of 6 are shown here. Next, the motion maps are max-spooled over the segmentation mask to produce 6 time-varying one-dimensional signals. Then we use the continuous waveless transform to decompose these signals into time-frequency spectra and estimate dynamic repetitive contents for each of them. Here we show 6 of these waveless spectra for an example video. As expected for this video, the vertical flow and the curl produce the strongest response. And we evaluate on the task of repetition counting, as a count remains meaningful in the presence of non-stationarity. And in this example, the acceleration of the rower after a couple seconds clearly shows up in the waveless spectrum as a drop in the motion period. And finally, we proposed a new CUVA repetition dataset consisting of 100 videos for the evaluation of repetition estimation. The dataset is significantly more challenging than existing ones, as we emphasize on non-stationary and non-static repetitive actions. To learn about our experiments, repetition, counting, and our new video dataset, please come to our poster at H1 next to the NVIDIA booth. Thank you.
Charles Falks. I'm here presenting on behalf of my student Shu Kang, who unfortunately couldn't be here. So there's been lots of progress in image labeling tasks and extending convolutional nets from image classification to richer outputs on individual pixels. Unfortunately, just classifying individual pixels isn't sufficient to model some output, such as labeling individual instances, since we have to decide on the number of categories in advance, and it's not invariant to permutation of the labels. So we explore the idea of, instead of using a discrete set of indicator vectors, labeling pixels with vectors in a continuous embedding space, where the idea is that pixels belonging to the same instance should embed at the same location in that space, and different instances should have different labels in the embedding space. To implement this, we use a convolutional network to embed the pixels in a spherical space and measure similarity between those embedding labels using the standard cosine distance. We can then characterize the quality of that embedding by asking that the pixels belonging to the same instance should have high similarity. Those belonging to different instances should be separated by some margin. So this is an idea that's been explored in supervised clustering and metric learning and recent work by associative embedding. To apply this to individual pixels, it's important to take advantage of issues of weighting the pixels based on the size of instances. And we show that by appropriate weighting and using spherical embedding, we can build an embedding loss function which is independent of the number and size of the instances in the image. So of course, just training with this loss function doesn't actually give you fixed labels in this space. So in addition, we add a recurrent grouping module which serves to collapse those embedding vectors for a given instance into a single label. This recurrent grouping module is built on the idea of mean shift clustering. So in the embedding space, we build a kernel density estimate and then evolve the embedding vectors to move up the gradient of that density estimate. The advantage of this sort of framework is that it's differentiable. The dynamics that move these embedding vectors towards a small number of discrete clusters and a few iterations can be learned so that the input embedding, that is the network predicting the initial embedding, can learn to focus on those places where the embedding vectors might have errors. So in this example, say 2 clusters, it focuses on those embedded near the boundary that won't be corrected by the grouping process. So this allows us to sort of train the whole model end to end and produce good grouping results. We've evaluated this on a variety of pixel labeling tasks, object proposal detection, and semantic instance segmentation, but also on some tasks which actually can be formulated as K-way classification problems. The main results that we show are in the problem of object proposal detection, where we show that by embedding and performing this recurrent grouping, we can come up with very good object segments. So we evaluate this by looking at the overlap of these segments with ground truth object segments and show that with even a few dozen proposals produced by the system, we can achieve high levels of recall that do as well as bottom-up segmentation processes that might require hundreds or thousands of proposals to achieve similar accuracy. We can take those proposals and label them with semantic labels here by just using a semantic segmentation and doing sort of majority voting to assign a label to each proposal, and this gives very good performance without ever actually invoking an object detection pipeline in order to find those instances. We also apply this to some classification tasks, so we can add this loss in addition to classification loss for semantic segmentation and show that this pixel-weighted instance loss solves some problems with pixel classification loss, filling in regions. We can even apply it to boundary detection, where the within instance is either pixels belonging to the boundaries or pixels belonging to the background. So here you're seeing outputs of layers of an HED architecture, the embeddings predicted from each individual layer. If we add a sort of fusion loss, which aligns these layers using the binary classification task, we can achieve very good boundary detection results here, which perform better than only training with a classification loss alone. So in this work, we're able to make use of that recurrent embedding in several different frameworks, give us an end-to-end trainable approach to pixel-level grouping. And this method's relatively simple. It has lots of interesting theoretical properties, so come by the poster to hear more. Thank you.
Hi, this is Chong from Australian National University, and this is a joint work with Qingnan and our advisors, Xiaodong, Haeffele, and Richard Hadley. I'm going to present our work on deep silence detection from a supervised learning perspective. What is silence detection? It aims to locate visually important pixel regions that attract human attention most, given an input image, and generate an output which highlights the silent objects. Based on the characteristic of silent objects, researchers propose to generate silent map based on low-level features, such as age and color information. Works in this fashion are usually considered as a bottom-up methods. Although they are cheap to implement and without any labeling information, the handcraft feature are not robust and are not robust to complicated scenario. For example, high contrast age and not all foreground, and the objects in background and the foreground may share similar color. On the other hand, with the rising of deep learning, people begin to use deep learning to solve this problem through incorporating high-level information. They introduced semantic information by using pre-trained model. Deep learning-based methods achieve much better results than bottom-up methods. Unfortunately, the downside is that deep learning methods require a large number of human annotation on each pixels. So we hope to develop a method that can achieve state-of-the-art performance as deep learning methods, but also get rid of labeling information. We start from employing semantic information by using pre-trained model on ImageNet and use the results of bottom-up methods as noise label to supervise our network at the beginning, and then refine the label in the following stage. As you can see, the Yij is the output of the J's bottom-up methods. Here. In our paper, we have 4 different bottom-up methods. These labels are not accurate and not consistent with each other. So how can we learn from them? So all the magic stuff from our widely used formulation in signal processing and the communication area. The observed signal is often considered as a summation of a true signal and the additive white Gaussian noise. In our setting, we denote Y bar I as the estimate silence map of image I, which is the output of our neural network. For a given image I, we formulate the noisy map Nij share the same distribution, where the variance is sigma I and the mean is 0. Here Yij hat is our estimate noisy label. Our framework is illustrated in the following figure. We simultaneously estimate the silence map and also the noisy distribution. At each round, we first approximate the bottom-up methods with our estimate noisy label, and then update the noise distribution based on the difference of silence maps and noisy maps. Our objective function contains 2 parts. We approximate the noisy label by minimizing the cross-entropy loss of label generated by bottom-up methods and our estimate noisy label. At the same time, we update our noisy parameter by reducing carrier divergency of estimate noisy and actual noise we get. This picture shows our estimate silence map for each round. At first round, the variance is 0, and we update the variance at each round. The corresponding silence maps are getting better. The following are the visual and the PR curve comparison of different algorithms, and our results are quite promising even compared to deep supervised methods. In conclusion, we propose an end-to-end silence detection without human annotation, which simultaneously estimates the noise and the silence map. Okay, thanks for your attention. Welcome to our poster session.
So, hello everyone. I'm Zhenqi Li from Cornell, and this is my work with Noah's Navy on learning intrinsic image decomposition from watching the world. Intrinsic image decomposition is a problem of factorizing an input image I into the product of a reflectance image R, capturing material color, and a shading image S, capturing the effect of illumination. Intrinsic images is a highly ill-posed problem, so using machine learning is a promising approach. However, unlike related learning problems like predicting depth or surface normal from a single image, we are not able to use Kinect or LiDAR devices to get ground truth decompositions for training data. So how do we get training data? Can we train a model without directly capturing ground truth decomposition for this task? In our work, we show how to train a model from time-lapse videos. We introduced a new dataset called Big Time with more than 200 internet time-lapse videos depicting both indoor and outdoor scenes with changing illumination over time. Here are some example videos from our dataset. During training, we take a self-supervised learning approach to ask a network to learn consistent decompositions from unlabeled time-lapse video clips. At test time, our trained model can use knowledge learned from time-lapse data to predict intrinsic image decomposition from a single photo. During training time, our system takes in a time-lapse image sequence as input, and we feed it into a convolutional neural net. The 2 decoders inside the CNN predict reflectance image and shading image for each frame in the input sequence independently. The key to our approach is our neural loss or energy function, shown on the right as E. We formulate this energy function as a continuous densely connected conditional random field over the entire set of reflectance and shading images. In our energy function, we can take advantage of the actual cues from time-lapse image sequences as implicit signal for learning. More specifically, first, we have an image reconstruction loss, which encodes the constraint that every image in a sequence can be reconstructed from its predict shading image, and any reflectance image is a sequence. Second, we know that reflectance should be the same across all the frames in a time-lapse sequence, and so we can directly encode this constraint in a reflectance consistency loss. Finally, we also introduce a new reflectance and shading smoothness loss, where smoothness weights between any two pixels depends on those pixels' relationship across the entire sequence. Therefore, we can draw on rich temporal information to compute smoothness affinities. Together, we find that these additional constraints are very effective in learning intrinsic images. We evaluate our approach on two standard benchmarks, IIW and SAW, which consist of images of real things with annotations created from human raters. In this plot, lower is better. Our predict decompositions have competitive or even superior performance on IIW and SAW, even though our network was only trained on our big time dataset. Some of these prior methods use classical optimization techniques, where others use supervised learning approaches. Our method outperforms both types of techniques. We also evaluate our approach on the MIT intrinsic images dataset, where we train our network on the image sequence provided by the dataset without using ground truth. We show that the decomposition predicted by our model outperform previous CNN-based supervised learning method. We have released all the data and code on our website, and thanks for your attention, and hope to see you at our poster session, H7. Thank you.
Hello, everyone. My name is Xiaodong Wang. I'm from National Institute of Health Clinical Center. I'm going to present our recent work on text image embedding network, TINET, and its applications on chest X-ray image annotations and diagnosis tasks. So in our last year's CVPR paper, we present a rule-based approach to annotate the chest X-rays so as to build a large-scale image data set for deep learning purpose. It could be considered our first attempt at using two-stage process based on traditional NLP techniques. Only reports are used in this case. So as a result, we produced and published a large-scale medical image dataset with over 100,000 chest X-ray images. All data are mined from NIH Clinical Center's PACS database. Compared to hand-labeled ground truths, those algorithm-generated labels surely can be further improved. So in this year's work, we want to improve the quality of the labels by using both the images and the associated reports, and using deep learning techniques. The rule-based NLP method is replaced with learning-based approach, and the NLP mined labels are used to initialize the learning paradigm. There are two main questions we want to answer here. Indeed, there are two different scenarios we want to apply the proposed TINET. The first one is how to generate more accurate disease labels for those images. And the other is to find a way to learn and somehow memorize the texture information or features so we can use them as a prior knowledge when we want to diagnose the disease using only images. So for this case, we designed a TINET network, particularly for those two purposes. The TINET is an end-to-end trainable network by combining the CN and RN structures together. TINET can take the common CN architecture as the backbone, such as ResNet 50. Multi-level of image and the texture attentions are applied for encoding the images and the texture features. And finally, two sources of features are combined for the final classification. The current format of the network shown here is for image annotation task. In this case, both images and reports will be imported for both training and the testing stage. As the AOC value showing here, it achieves a real high accuracy of annotating images in both our own testing set and the other two hand-labeled data sets. In addition to the image annotation task, The proposed TINET architecture could be further transformed into an image classifier and a report generator, when only images are imported during the testing. In this mode, the LSTM model are switched to a generative one. A radiology report will be output in addition to the image classification results. Compared to the benchmark, the proposed method is able to improve the classification performance on all 3 different testing sets by a clear margin. 4 sample results are showing here. The generated reports together, the original reports are showing at the bottom. Textual attentions are highlighted in red. The content described in the generated reports are strongly associated with the classified disease word, which is a desired feature of our proposed TINET. So if you have any questions or want more details, see more results, please come by to our posters. Our poster number is H9. Thank you for your attention.
Hello, my name is Brian Texera and I work for Siemens Healthineers. This presentation is about generating synthetic X-ray images of a person from the surface geometry. From the 3D surface mesh, which could be estimated using a depth surface, depth sensor such as the Kinect, a framework generates the corresponding synthetic X-ray together with a set of anatomically meaningful landmarks, which could be used as control points for updating the X-ray. We compare our synthetic X-ray with real X-ray scans. On the left part of the UI, you can see the surface mesh used to generate the synthetic X-ray on its right. The same image is displayed on the right, together with the predicted landmarks. We can actually move these landmarks to update the X-ray in real time. As you can see, our framework only allows realistic configuration, and if the landmarks are moved to unreal position, the synthetic X-ray stays realistic. Finally, if we move all the landmarks to arbitrary position, we can still use the X-ray to refine the landmarks and retrieve a consistent configuration. Here, the ground truth X-ray displayed on the right has longer lungs compared to the first prediction on the left. In case we have the ground truth landmarks, which we could obtain using another acquisition such as MR, we can move the firstly predicted landmarks so that they match the ground truth and use these new markers to generate a more accurate X-ray image. From the surface mesh, we generate a first estimation of the X-ray, which we then combine with the surface again to generate the markers through the marker prediction network. These markers are then combined again with the surface to generate an updated X-ray through the conditional image generation network. We repeat this process iteratively until both MPN and CIGN converge to a steady state. To enforce consistency between MPN and CIGN, MPN gets updated on how well it helps CIGN in its regression task and also on its own tasks. CIGN acts the same and also gets updated using MPN loss together with its own loss. Here we train both models together so that they converge to the same solution. Here you can see some results on the testing set. Even though our results are not as detailed as the ground truth, especially on the spine area, which is highly subject to variance, the resulting images are still pretty realistic. It was of course not able to guess the metallic implant of the first patient in the first column. One possible application of this framework could be training data generation. Medical data is really difficult to acquire. We just investigated the usability of our framework for training deep neural networks. So first, we annotated the left lung bottom landmark, which was missing in our original set, and we generated random translation as a baseline for augmenting the data. We did exactly the same thing with our parameterized set and moved all the landmarks within closed range, resulting in a new augmented data set. Finally, we trained exactly the same network with the same random seed on the 2 different training sets. As you can see, the network trained on the parameterized set converged way faster and had lower Euclidean distance. You can also see a result on a challenging image where the detector trained on the translation set failed, but the one trained on the parameterized set correctly located the landmark. As our framework was trained using only healthy patients, we can use the synthetic X-ray images to detect anomalies on X-ray scans. Here, for example, this patient has no left lung. We can then generate a synthetic X-ray and compute a difference overlay, which clearly shows the missing lung. In case the patient has no visual salient pathologies, when we'll generate the synthetic X-ray and compute the difference overlay, it will not show anything, saying that no visual salient pathologies were detected. Another really common anomaly on X-ray scan are metallic implants, which may also be easily detected using our framework. Thank you so much for your attention, and please feel free to visit our poster at H11.
So good afternoon, everyone. I'm Amir Zamir, presenting Gibson Environment, Real-World Perception for Embodied Agents. This is work done at the Stanford and UC Berkeley with Fei Xia, Jiang He, Alexander Sachs, Jitendra Malik, and Sylvia Soares. So traditionally, computer vision is learned using data sets, but we need to develop perception models for agents that are physically active in the world, like robots. The conventional data sets are lacking for this purpose because they're obviously passive, so the camera location or content cannot change according to agent's actions. So you could learn perception with a physical agent in the physical world with an onboard camera. This approach has some drawbacks, like learning speed is bounded to real time, obviously, and important but critical events like a car crash cannot be freely repeated, and working with robotic hardware is often time consuming. This has given rise to learning in simulation as an alternative approach. But using simulators often has the concern of generalization to real world. So focusing on vision, there are two main challenges about generalization from simulators. The first one is photorealism. So when you look at renderings coming from simulators, it's obvious that they are not coming from a real camera because they show some imperfections. But this potentially can be alleviated as computer graphics gets better and domain adaptation methods improve. A bigger issue is semantic distribution mismatch. So the models used in simulators are usually hand designed and artificial, so they do not really reflect the semantic complexity of real world. This is not an issue that can be improved or alleviated with any adaptation method. So we propose Gibson to get around some of these issues. So here's Gibson at a glance. There's a larger space. There's an active agent in it that can freely move around. The agent receives a stream of RGB frames as if it had an onboard camera, and some additional modalities like semantics or depth. It's also subject to constraints of physics like gravity and collision. Here you can see, for instance, a Husky agent that is virtually driving around Stanford's Gates building. It hits the walls a few times and struggles, and ultimately it stops right here. All right, so here's some more details. So there are 572 buildings in Gibson's database. These are all real full buildings. They are not synthetic, and they are scanned with 3D scanners. They can be explored in Gibson Simulator. On the right, you can see some random explorations, for instance. And you can import an arbitrary agent if you have its URDF. And the physics constraints are enforced by integrating PyBullet physics engine. Now, to provide that RGB frames from arbitrary viewpoints, we developed a novel neural network-based view synthesis engine. I'm sparing most of the details for the poster session, but it's faster than real time, and it has a baked-in mechanism for transferring to real world that we call goggles. Okay, so some more examples. On the left, you can see, for instance, a turtlebot that is going from living room to a bedroom that you can see right here. And on the right, you can see a Husky agent that is driving around the living room. And yeah, all right. So these are some sample perceptual agents that we developed in Gibson using reinforcement learning. On the left, you can see a car that is doing visual obstacle avoidance. On the right, you can see ant traveling down a stairway visually, and some car traveling distant location. Yeah, this was an overview of Gibson environment for learning perception based on virtualizing real world. You can access it from our website or GitHub.
Good afternoon, everyone. My name is Le Yang from Northwestern Polytechnical University. I would like to share our work named Reinforcement Cutting Agent Learning for Video Object Segmentation. Let us begin from the background on our work. According to former research, when searching or localizing objects, biological vision systems are found to change retina fixation sequentially. They gradually accumulate evidence of certainty and finally make a precise decision. We believe it does the same for segment objects. We want to explore a similar pipeline by sequentially exploring the desired object mask and consider the corresponding context information. We resort to the deep reinforcement learning series, which had been demonstrated its effectiveness on globally optimizing the sequential models without supervision for each step. However, learning agents for segmentation is now trivial because segmentation is a nearly continuous decision-making process, while the number of the involved agents or action steps from the beginning seeds to the whole object mask might be incredibly huge. To overcome this difficulty, we simplified the learning of segmentation agents to the learning of a cutting agent. The basic assumption is that object segmentation mainly relies on the interaction between object regions and their context. Thus, with an optimal object region and a context region, we can obtain the desirable segmentation mask through further inferiors. Based on this assumption, our cutting agent consists of a cutting policy network and a cutting execution network. The former learns policies to deciding optimal object context box pair. The latter executes the cutting function based on the inferred box pair. Let us see the framework of our approach. For video object segmentation at each frame, the cutting policy network observes the current states, determines actions to adjust object box and context box. Then, the cutting execution network generates the object mask of refined box. With the collaborative interaction between the two networks, our model can progressively improve the segmentation performance. Now, let's analyze some details about our work. This is the network architecture of cutting policy network. The two-head branch generate object box action and context box action, respectively. This is the network architecture of cutting execution network. We directly using a fully convolutional dense net architecture. We achieve satisfying performance on Davis 2016 datasets under 3 different methods. This is a visualization about our method. We gradually obtain precise mask. In the end, I want to show specific acknowledgement for my supervisor. Thank you. And for details about my work, please come to H15.
So that was the last spotlight talk in the session. I'd like to thank all of you for your attention, and I'd like you to all join me in thanking the speakers one last time.